nominal.
RCP chamber pressure looks good.
Doubling up. Roger, roll, Atlantis.
Water towers can fly! Yes!
Tango Delta nominal.
Flight outside feed off. Bring in, SCE off. Off.
Yikes. You bet. Concur. We don't need any more of these.
All right, folks, you know the drill. You saw the intro, so you know what time it is. Let me know if you can hear me and see us here. It is time for another NASA Spaceflight Live. The bar's jumping, so I'm hoping that the audio is coming through. Who knows? I've been gone for a while, you may have noticed. But again, it is time for another exciting episode of NASA Spaceflight Live. It is our weekly show. We do just about every Saturday, unless something else is going on. And we've got sort of a continuation show happening today. A guest that we have had on before and back by very popular demand. Y'all say a good NASA spaceflight welcome to Jonathan McDowell. Jonathan, how are you doing today?
Very good. Thanks, Des.
All right. Chat, did you get Jonathan there? Let me know that you could hear him and see him as well. And then also joining us, Chris Gebhardt, Assistant Managing Editor for NASA Spaceflight. Chris, how are you doing?
I'm doing great and excited to be back and talking with you today, Jonathan.
All right.
Good to be back.
Deal. So, folks, let me know. You got Chris, you got Jonathan. We are going to get started here. A couple housekeeping things before we do. Remember, it's a live show, so we are making this up as we go. It's sort of like our video-enabled podcast thing. We don't have an agenda or script or anything. Got some topics we're going to talk about, but it is live, and you're part of the show. So if you have questions for us, questions for Jonathan, put them in chat. And when you put them in chat, tag us at NASA Spaceflight. That'll put them in some nifty software that we've got here on the screen, and we can scroll through and grab some relevant questions and pass them on to Jonathan. But make sure you tag us. If you don't tag us, it's probably not going to get seen because we get tons of chat scrolling through. Also, with special event shows, I know that y'all support us. That's why we're able to keep showing up. But we don't read super chats during special event shows. So even if you put in a super chat, we do appreciate the support. That's why we can do this. But to focus 100% of our time on the guest and hanging out with the guest, we don't spend time going through the super chat. So we appreciate the support. We're able to do it because y'all keep doing that, but just be advised those are things we don't read through. Beyond that, like I said, if you have questions, make sure you tag us. And Chris, Jonathan, we ready to go?
I think we are.
All right. Well, I will let you take it away, Chris, and then I'll click on things in the background and show pictures and stuff like we do.
Yes. So, Jonathan, thank you so much for coming back because we had so many things that we wanted to talk about last time that we kind of ran out of time for because we had so many questions and such great discussion about so many topics. But before we delve into, because I know people have a lot of questions about Starlink and mega constellations, and we're going to talk about where the boundary to space begins and what makes an orbit an orbit. But I did definitely, one thing I was really sort of disappointed at that I didn't get to last time was all of your work outside of what people, usually interact with you for, on Twitter and tracking China space debris and, and when something seems to be falling out of the sky. But, I wanted to talk about your site, the Space Report, and I also wanted to talk about your work with X-ray astronomy and everything. But I really wanted to talk about the Space Report first because for anyone out there who isn't familiar, this is an amazing resource that I know probably all of us in the industry reference a lot. It's filled with the historical archive of launches and other sorts of information and your newsletters on things. What was sort of the impetus that led you to develop this this incredible resource?
Well, I actually, when I was about 12, I started making this list of rocket launches, and as many kids do, but I just stuck with it and got deeper and deeper. And then when I started work at the Center for Astrophysics, back in the 1950s, the Smithsonian Observatory, that's part of the CFA, it was the place to ask when you wanted to know when Sputnik was going overhead, right? But all the people who did that kind of stuff had retired. We weren't doing it anymore. And so our public affairs people kept getting these press inquiries or public inquiries about satellites, and they kept bugging me because they knew I was the guy who could answer them. And so I started writing the report as sort of self-defense here, guys, this is what you're going to get asked this week. And then someone said, you should put this on the internet. because there might be at least 5 other people who are interested in it, and,
At least.
and so the rest is history.
I like how you said in self-defense, like, I'm going to put this out so that I don't have to answer the same question 15 times. And now it's like answering the same question 500 times a week, especially as we get into these, is it orbit, is it space or not things, right?
but you know, like it is a truly valuable resource because, you know, there was a question that I was trying to answer a couple of weeks ago regarding the original tracking and data relay satellites that NASA used to launch out of the payload bay of the shuttle with the IUS. And I was trying to figure out, like, which stage did the inclination change, which stage was, you know, and how all of that worked. And it was honestly your space report, because it had the initial, it had everything, like, of where all the stages still were that were made it very, very easy to go find some of that stuff. I mean, it's an incredible amount of work, and it's an incredible project. I mean, and it's still a lot goes into keeping it up, doesn't it?
Oh yeah, and wait till you see GCAP version 2 that I'm hoping comes out late this year, early next, where you'll have the sort of mission logs for every satellite, so you'll be able to find that kind of information even easier. So yeah, it is. I mean, I did a lot of work in my teens and at college, you know, collating historical information, and got it to a point where then I was just, my internal files, you know, it takes me a minimal amount of time to keep it up because I've got it down to a fine art. And so the hard work is formatting it and referencing it and you know, making it robust for people to use. And that's why some of the stuff that I've done, you know, has only come out in the past year, because it just took me that long to properly document it and clean it up.
No kidding.
Wow. So that's another thing that people do really know you for. But I also want to talk about the scientific research areas and your scientific research. And I want to start with the Chandra X-Ray Observatory, because this was by far, you know, a fantastically revolutionary tool for the field of X-ray astronomy. So I was hoping that you could talk to us a little bit about your involvement in the project to start with, and what some of the more impressive findings have been, in your opinion, from this ongoing mission.
Right. So Chandra is the best X-ray telescope ever, right? And it's to be specific, it takes the sharpest X-ray images, and so it's Chandra is a cousin of the Hubble. It's one of the NASA's great observatories. We developed it to follow on from our earlier spacecraft, the Einstein Observatory, back in 1970, before my time, the Uhuru satellite that was the first X-ray satellite. And we really realized we needed a telescope that could take pictures that were comparably sharp in X-rays to what typical visible light pictures were. And so that was the key design of Chandra. And the trouble is, you know, so where I'm studying quasars a billion light years away, these X-rays come across space for a billion years, and then in the last second, they're stopped by the Earth's atmosphere. And so just by poking your nose above the atmosphere, you can catch them. You can see so much farther. And so Chandra isn't one of these missions like, for example, Planck, where there's one targeted science question. It's much more like Hubble. It's a Swiss Army knife tool for astronomers across the world to use to answer all kinds of science questions about the energetic universe. And so my way of sort of thinking about Chandra is, you know, Hubble sees the ordinary parts of space, the boring parts of space. Chandra sees the 10% of space that's going badly wrong. and so we see exploding stars, we see matter falling into black holes, we see super hot clouds of gas, and so that for me is the exciting part about Chandra. And we had one of the big questions we had for the earlier X-ray missions was we saw this glow all over the sky in X-rays, a bit like an X-ray version of the cosmic microwave background, if you're familiar with that.
Oh.
That turned out to be the glow left over from the Big Bang. And so the question was, well, what's this X-ray glow? Is it something like that, which is a really diffuse thing coming from early in the universe? Or is it just a lot of pretty distant X-ray sources that are all blurring together because our telescopes aren't good enough? And so Chandra answered that. It turns out that, it's actually an awful lot of faint black hole accreting sources, quasars and active galactic nuclei, that were too faint to be resolved by the earlier telescopes. With Chandra's exquisite vision, it can actually pick them out one by one and account for that earlier glow that was seen. And so that was one important discovery. Another important one we're just showing on the screen right now is that's the bullet cluster. And so when you have a cluster of galaxies, you have about 1,000 or more galaxies all hanging out together in each other's orbit. But actually, it turns out, as we discovered before Chandra, in X-rays, if you look at these clusters of galaxies, what you see is one big blob of gas. That actually a cluster of galaxies is not just 1,000 galaxies hanging out together. That's a footnote. What's really going on is that there's an enormous dark matter halo containing an almost as enormous hot, like 10 million degree hot gas halo. And then there's some galaxies in there as an afterthought that are hanging out in this enormous cloud of gas. But you can only see, because when matter is at millions of degrees, it's transparent to ordinary light, but glows crazy in X-rays. You don't know that stuff is there until you have an X-ray telescope.
Until you look at it in X-ray.
Right.
Gotcha.
And the particular observation that Maxim Markovich and his friends made with Chandra of that what I call the bullet cluster is when actually two entire clusters of galaxies, each of which has a mass of 1,000 trillion suns, have smashed into each other supersonically and are passing through each other. And there's an enormous shock wave going through. It's the biggest train wreck we know. And what happens there is that the dark matter in each cluster sort of feels the gravity of the dark matter in the other cluster and slows down a bit. But the gas feels not just the gravity, but the shock wave, that it interacts more directly with electromagnetism. And so it separates out from the dark matter. And so in that cluster, the dark matter and the visible matter are not in the same place anymore. And we can detect the dark matter by its gravitational lensing, and we can detect the ordinary matter by the X-rays and show that they're not in the same place. And that shows that dark matter is a real thing and not just some weird error in the law of gravity.
Like we've just made it up to account for something that we don't understand, right?
Right. There were some people who tried to go, well, maybe we can make the dark matter go away by making gravity not 1 over r squared, but 1 over r squared plus a little bit if you're on a really big scale.
Right.
Right. And the fact that we can actually sort of see the dark matter separate from the ordinary matter says, no, that ain't what's going on. There's really a thing there that we can't see that's exerting gravity. So that was one of the major discoveries of Chandra. But we've also, found a lot about supernova remnants, exploding stars, where we're all made of stardust, right? And so the freshly made atoms that are going to make the next generation of stars and planets, we can see with Chandra because they're really hot just after the supernova explosion. And so they shine in X-rays.
That's something I had never thought of before. I mean, you said gravitational lensing, and we're talking about Chandra, but
that's the bullet cluster again there, yeah.
Yeah, I know, gravitational lensing, like you can see, this visible light, and it's getting bent by something, but I guess that also affects X-rays and other forms of radiation, right? Does everything get gravitationally lensed by whatever's out there?
Oh, sure. I mean, X-rays are just light, a color your eye can't see.
Right.
And so yes, gravitational lensing acts on all colors of light,
everything, all electromagnetic radiation, or whatever the right way to say it is, right? Huh. I just never thought about that
Oh,
before,
wow.
but so many of the pictures we see, like we see all of these graphics, and they're not always visible light. They've been changed into something that we can see, but when they're coming across the universe, they're X-rays or some other form of radiation, right?
Well, that's right. If you only look in visible light, right, when these things in space are making all the different kinds of light,
Right.
then it'd be like walking around town and you could only see things that were colored blue.
Right.
And anything that was
Mhm.
colored red or green, you wouldn't, which would be bad if you went through a stoplight. So, so we have to use all the different kinds of light to understand what's going on out there.
Right.
And some of them, like visible light and radio waves, come all the way to the surface of the Earth. And others, like X-rays and far infrared, get stopped by the atmosphere. And so you have to put your telescopes outside the atmosphere to see them.
Gotcha.
So, and that's actually one of the interesting things, because I think a lot of people are used to the fact that the Hubble telescope is in low Earth orbit, partly so that it could be serviced by various missions. But I think when you said, like you peek out above the atmosphere, but Chandra's really up there. I mean, it's in something like a 14,000 by 136,000 kilometer orbit. Why such an eccentric orbit? Why such an orbit so far away from the planet, even at perigee?
Right. Well, because we wanted to spend most of our time outside the Van Allen belts so that we get a nice low background. And also that we wanted to be able to study X-ray sources for a long period of time without the Earth getting in the way. And so because the things, there's so few X-rays that reach Earth from these things, we have to expose for a long time. If I take a photo of you with my cell phone, right, the exposure is like a quarter of a second or something ridiculous. If I take a picture of a cluster of galaxies with Chandra, we hold the shutter down for about a day and a half. We go, okay, we got another X-ray at 3 p.m. and we expect the next one at 3:15 or something like that. So really these things are so faint that we need long exposures, and it helps being out in deep orbit for that. Also, it meant that we couldn't be serviced by the shuttle, and therefore we didn't have to human rate everything. So that's actually a plus in terms of the cost of the mission and things like that. That was a really exciting thing. And mainly it's low background was the key thing.
Gotcha.
I would really prefer to be at like L2 or something like that.
Yep.
At a Lagrange point, but we didn't have a big enough. We couldn't afford the rocket, so the elliptical orbit was a compromise, and it was the sort of fashion at the time. There have been sort of fashions in astronomy satellites that when the shuttle was like going to be the big thing, then everything like Hubble and everything else went into low orbit, so it could be serviced.
Right.
And then we had a phase where but also our European counterpart XMM Newton and the gamma ray European satellite Integral went to these big elliptical long orbits. And then the infrared Spitzer folks realized, well, actually, if we boost a little further, we can get into solar orbit. And then we're even further from Earth, and you don't have to worry getting in the way. On the other hand, you lose communication after 5 years because it's drifted too far away. So that wasn't ideal. And so then people went, oh, well, L2 is the place to go. Because if you're at L2, you have the Earth and the sun behind you and the darkest part of the sky ahead of you. And it's just perfect for astronomy.
Right.
And that's why Webb's going there.
And that's where, Planck and Gaia and Herschel and a whole bunch of other satellites have gone there in the past decade or so. And Webb is going there too, because it's just, once you kind of get used to operating at L2 and have big enough rockets to send a decent payload there, that's the place to send your astronomy satellites.
Mm-hmm.
Gotcha. What's the orbital period of Chandra? Is it like 2 days?
It's 2.5 days.
2.5 days. Okay.
Yeah.
So when you
go
say,
around the world,
yeah, go ahead.
yeah, we of that, about half a day is spent going through perigee. So Kepler's second law, as many of our listeners will know, right, says that in an elliptical orbit to first order, basically you spend almost all your time hanging out at apogee. And then every now and again you go, Fa-choom!
It makes that noise, actually.
Yeah, right, round through perigee. And so, but it's much faster at perigee, so it doesn't take as long.
Yep.
So most of our 2.5 days we spend out at apogee. but then we spend, you know, half a day or so going through perigee where we have to switch off the cameras because of the radiation in the radiation belts.
So every 2.5 days, you're switching off and the telescope's been doing this for over 20 years at this
Actually,
point.
not only switching off, moving the camera out of the focus of the telescope.
No kidding.
Because
Like
we didn't realize we'd have to do that when we launched. And in the first few weeks after launch, we suddenly realized, we're getting horrible radiation degradation in our CCD cameras. Our spectral, you know, our science resolution is going down 1% a week or something, and we're toast if we don't fix this.
Yeah.
And we realized, not only does the telescope focus X-ray light, it also focuses soft protons in the radiation belts. We had actually built a machine to destroy X-ray cameras accidentally. And so once we started every orbit moving the camera out of that beam of radiation, we did a lot better and the damage stopped. So
it's a good thing that was built in. I mean, is it physically, like the camera physically moving, or is it a shutter?
A little train called the science instrument module, because we've got two cameras.
Yeah.
And so you can move either one into the focus.
So they just scoot out of the way so that they're not in the focus when you swing through the radiation belts. And then
exactly.
Everybody understands, like when we say elliptical orbit, I know we need to move on, but this is like our quick explanation. Everybody understands when we say elliptical orbit what we're talking about, right? Like imagine you have the Earth. I'm going to get to telestrate here. And this is the Earth. And what Jonathan was saying, you know, holding down the shutter for a day and a half, it takes 2.5 hours or 2.5 days to complete an orbit. It looks like this, and I can't draw ellipses to save me, but you have sort of way up here, and as you sort of orbit down, it's going to come down, but it goes faster and faster, and then it swings around, then it comes back up here again, right? And so I don't know the exact timing, but Jonathan, the velocity when it's down here is very high, and the altitude's very low. And up here, the velocity is very low, and the altitude's very high. Right?
Exactly
the
right.
Energy is the same at all those points because that's how orbits work, right? But that's how you get this really long time sort of between here and here, and then it swings back by the Earth really low again, and it swings way high, and you get all this time to leave the shutter orbit where you're not dodging the Earth, you don't have to move the camera for the radiation and stuff like that, right?
Exactly. If you imagine throwing a ball high into the air, right?
Yep.
There's this moment where it kind of seems to just hang.
Yep.
Before it starts falling again, it moves very slowly right at the top. And so it's just an extreme version of that.
Yeah, I went off the top of the screen there, apparently. But it's just gravity. Gravity's constantly pulling on it, and then it slowly overcomes it, and it starts to fall again. But anyways, I wanted to, that was something we could draw really quickly for the people that maybe don't understand. What's an elliptical orbit? How does that help the science instrument? It gives it all that time out of the radiation, this big long arc that it swings through, and that's when you can leave the shutter open for a day and a half, right?
Right, exactly.
Cool. All right, I'm done drawing.
So, well, we have a couple questions about X-ray telescopes and X-ray astronomy from some folks. Ron Smith, in particular, is asking, MAXI is an X-ray telescope on the ISS. So, based on what you're saying about proximity to Earth's atmosphere, would an exact copy of that on the Lunar Gateway function better than the copy that's on the ISS?
Well, in some ways, yes. It wouldn't be blocked by the Earth as often. So the radiation belts, right, are bad till you get above geo or below 1,000 kilometers. So the ISS is actually below most of the radiation.
Right.
And so, but the problem is that it's just whizzing around the Earth every 90 minutes, and the Earth's going to get in the way of a lot of the bursts.
Hard to keep the shutter open, right, for a day when you're every 90 minutes.
Right. So it's limited in its view, but also MAXI is, you know, it has a very broad, fuzzy way of looking at the world. It's not like a sharp vision of Chandra. And what it's looking for is incredibly bright bursts of X-rays that are sort of nuclear explosions on stars that might come from any direction at any time.
Right.
And so it's sort of a early warning alarm, right? And so it doesn't need to be so sensitive because it's looking for like things that would totally blind Chandra. And so then, you know, MAXI goes, oh, this thing went into a burst. And maybe Chandra decides, okay, we should go and look at this in more detail then.
It's almost more of a strategic overview of what's going on instead of like tactically looking at one focused thing, right?
Right, exactly.
Gotcha.
And another question here too from one of our members, a regular Dank Jeb. He's asking, or they are asking, is there any plan to replace Chandra with an upgraded version or like a new X-ray astronomy?
Thank you for that question. So we are actually on tenterhooks right now. Every 10 years, the astronomical community has what's called the Decadal Survey, which picks the next big projects that they're going to recommend that NASA develop. And right now we're waiting to hear what the Decadal has decided from various projects that have been put forward, one of which is a fantastic project called Lynx. And Lynx is a super Chandra. It has a sharp vision as Chandra, but over a much wider field of view.
Oh, wow.
As well as more sensitivity. And so it would basically be a much faster Chandra instead of having to, especially if you're looking for, surveying the sky, you can get a lot more data in the equivalent time. And
is it sort of analogous to like how Hubble does the deep field looks every once in a while, but you can get a lot of information about a lot of galaxies in that one observation period?
Exactly. And Chandra does deep fields too, but it takes, a couple weeks of observation, right? And you'd want to be able to do that with a wider field of view and in a much less time. And so, yeah, Lynx is a great project. I really hope it gets picked. Even if it doesn't get picked by the Decadal, I hope that we find some other way to push it forward. But as of right now, there is no funded successor to Chandra. And Chandra has been going for 22 years now. 22nd birthday's coming up at the end of this month.
Yes.
And so, and it was originally, spec'd to be a 5-year mission, right? So, so Chandra's old, and it's showing its age. I mean, it's still doing great science.
Right.
We have to work really hard to get the same science done. We've lost some sensitivity in certain energy ranges. The thermal insulation's cracking and peeling off, and so we can't do long looks anymore. We have to stitch them together from short observations and then go cool down, pointing somewhere else.
Mm-hmm.
And there's various systems of degrading slightly, not enough to stop us doing the science yet. But, at some point, we're going to have to retire Chandra. And we really should have had a funded replacement in the works 10 years ago.
Yeah.
So it's a big issue.
Yeah. I don't want to get too far into it, but with the Decadal Survey and stuff like that, is that like a committee that votes on all these proposals that are put together? Or is it like one person that's like, I think this looks like a cool spacecraft? Like how do they choose? Like there must be so many good ideas.
It's a committee, and you they get these big books from all of the mission teams that they kind of review, and then they write a report ranking them. So it's just like any any proposal review committee, except the stakes are enormous.
Yeah, once a decade. Jeez, that's the name, I guess.
Exactly. And Chandra was the choice of the 1980 Decadal, and it actually flew in 1999.
Wow!
So that gives you an idea of And then Spitzer, I think, was the 1991, and it flew in 2003.
Jeez.
So these projects take a long time to develop, and the stakes are huge.
No kidding.
Yeah, there is one thing I think I'd be remiss in the community if we didn't get your thoughts on, though. It's not exactly the X-ray astronomy goddess that Chandra is, but it's the other one that's really near and dear to all of our hearts. What are your thoughts on their continued efforts to get the Hubble back online, and what's the plan if they can't?
They will. I am
there we go.
confident that Hubble will be back doing science. I have the team that they have right now at Hubble. I know a bunch of them very well. They're really good. So there's a lot of redundancy left. there's a lot of failure tree to work through still.
Right.
And they're just going at it very deliberately and very slowly, as you know, as we always do, right? And working out, maybe it isn't this processor, maybe it's this thing further up the chain that's actually causing the problem, and that's why we're seeing it on both sides.
Right.
And so it's going to take some time, but I'd be really surprised if they can't get it back up and doing science in about a month.
Gotcha.
It might take that long, but and so we have these. I mean, it's very scary when your spacecraft is sick. It's like having a kid sick, I guess. It's like,
Right.
Yeah.
Even if you know they'll get better, it's still frightening. And so we but on the other hand, Hubble's really old, right? It was launched in 1990, and it was last serviced when 2009 was the last.
Yeah.
Yeah.
Right.
Yeah.
So it's been 11 years since John Grunsfeld last kicked it. Sorry, John. And so at some point it is going to die.
Yeah.
We need to replace all the things.
Mm-hmm.
And I think one of the problems I have with the decadal process is that they tend to pick the one most expensive project
Ow.
instead of going, okay, yes, that can do more science than any one of the other four you might have picked, but why don't we pick four less ambitious projects that would cover infrared and X-ray and visible, and maybe each one would be only an incremental step beyond Hubble. But you know what? Hubble's pretty good. So
right.
rather than having to make a factor 10 improvement every time, which always leads you to having to spend extra billions, so that's my concern, is that we'll be left either without a Hubble or without a Chandra, and that you really need both, right? Because you need to see in color.
Mm-hmm.
You need to see all the colors, and so if you have to wait 10 years to get the follow up in the other, if you're trying to take an RGB image, right, and for your and someone tells you, okay, well, you can take the R this year. But for the G, you're going to have to wait another 12 years.
Another 12 years, gosh.
Right? That's not so great. And so I really hope that we can find a way to fund maybe not the most ambitious projects you can imagine, but good, solid observatories that can cover the range. And this is one thing that is always a tension between astronomy and like particle physics. In particle physics, they've always had the tradition of, well, we have to push the energy to the absolute max. We want to find the Higgs, we want to find the supersymmetry or whatever. So you build the biggest collider you can imagine.
Right.
And astronomy is not that science. Astronomy is the science of like many small projects in general, rather than the one big project.
Gotcha.
And so you want a whole bunch of different tools to address the science.
Yeah, a bunch of singles and doubles instead of swinging for the fences, I guess, right?
Yeah, but sometimes it's the singles that get it, right? One of the big discoveries, right, was from things like the COBE and the WMAP microwave background satellites, which were relatively small explorer missions and not flagship missions.
Right.
And yet, that was Nobel Prize stuff. And so so it's not always the big missions that give you the most spectacular results. They always give you great results, but you need the other smaller stuff as well.
Yeah, makes sense. All right, Chris, we're 35 minutes in talking about X-ray telescopes and stuff. We still have a lot of other topics to cover as well, so let me know when you're ready for the next big thing I'm putting on the screen here.
Yeah. So, so this is one that I think a lot of people still have a lot of questions about. But I want to start with a brief recap on the mega constellations that are currently being launched. And so I wanted to briefly recap what we had talked about last time that you were on, where you were talking about, and we were showing graphics about how, the initial fear that the Starlinks would be really, really bad for astronomy might not have been panning out as devastatingly as had been thought. That yes, in some of the telescopes in the southern hemisphere, Chile and Argentina, midsummer months, yes, you'd have a lot of effects in the twilight periods, but you still got some good observation time in the middle. But then, and Das, we're going to start with the but then.
But then, oh wait, but then? Wait, the
Yes,
second
we're
one
gonna
or the
start-
first one?
We're going to start with the second link.
Okay, well,
Yes.
here you go.
But then we had something else after ours, where you had this tweet that said about 30% of the Starlinks were in their orbits, but about 66 were still being raised. And this was very different than what was originally thought, and it could have some impacts on astronomy. So let's restart that entire conversation.
Well, let me say, yeah, and the important thing is it's not just Starlink.
Right.
And I will say that SpaceX have been among the most responsive of the companies in trying to reduce the impacts. And so I think there has been progress, but we're still scared, is the bottom line. And we're having a conference, in fact, in just over a week starting on July 12th, the SatCon 2, at which astronomers and the companies will get together and discuss mitigation strategies and problems and try and understand better the threat. And so this has actually been a lot of my work over the past few months, has been preparing for that and trying to update our understanding of what we can do. And so there have been some good developments. So one good development is that SpaceX added the visors to the satellites last summer, and they changed the attitude control a bit. And so the satellites in their operational orbit are fainter than they were, which means that they're not going to be naked eye objects for the most part. They're going to be just like only a really dark sites, barely naked eye.
Right.
And so I'm less concerned about the impact on naked eye astronomy, although, as you say, there's a lot of, in the orbit raise phase, there's a lot of them, and they are pretty bright. So I think it'll be annoying, but not disastrous. For professional astronomy, where we obviously are looking at things that are much fainter, it's still potentially a challenge, but not as much of a challenge as for the OneWeb constellation, because the OneWebs are in higher orbits, and so they are illuminated longer into the night, all night long in summer, and they're visible. Each satellite is visible from a wider area, and so those two combinations mean that for an equal number of satellites in the higher orbit compared to the lower, the effect is much, much, much worse. And so the OneWeb constellation is a big threat to us, except that post bankruptcy and restructuring, they've restated their plan. So they're no longer planning, they say, to launch 48,000 satellites,
Right.
but only about, I think I remember 5,000 or something like that, some smaller number that does cut down the impact somewhat. But then again, China has announced that it has a 13,000 satellite GW constellation that it's going to start launching. That's going to be in similar high orbits, a lot of them. And so when you add that back in, we're back into being screwed. And so we're still very much trying to understand the detailed impacts on different kinds of science. For example, one thing that we didn't anticipate earlier is, even though, so a lot of very crucial science is done by what we call fiber spectroscopy, where we take a whole bunch of optical fibers and point them in slightly different positions in the sky, and the light from individual galaxies goes into a spectrograph, and you get what's called a spectrum, which enables you to measure the redshift and things like that.
Right.
But if a satellite passes over, you're adding basically a solar spectrum to the spectrum that you were trying to study at some low level, but it's enough to change the answer.
Right.
And
have
you
to
have
deal
no
with.
way of knowing that this happened, right? Because you've got no spatial information. You just right. And so you really need to know whether or not a satellite passed over your fiber or not. And so even though the fibers are a small area on the sky and they don't get hit as often as a big wide field detector, instead if you have a wide field, low spectral resolution fiber spectrograph, you're gonna get hit some of the time and you're gonna maybe not realize that you were hit.
Gotcha.
And so you're going to get wrong answers. We already recently, and since we last talked to you, there was one paper that had to be retracted because they thought they'd discovered a flare in a super distant high redshift galaxy, and it turned out that in fact it wasn't. It was an old Soviet rocket stage.
Oh.
It wasn't a mega constellation satellite, but it was a satellite that passed through the field of view at the right time, and they like tried to check for that, but they hadn't done a good enough check that included high orbit satellites, and so it turned out that a far more likely explanation for what they saw, and it was a very exciting scientific result if it was real, right? But that's exactly the kind of time where you go, yeah, is it really real, or am I being fooled? So there are real cases where I mean, the point is this: if you get Starlinked, right? If you get affected by one of these things and you fail to detect it, it's almost certainly going to look like something really exciting.
Right.
Right, because it's going to cause your star or your galaxy to do something that it wouldn't normally do.
Right.
So you're going to publish this paper and then have to, really red-faced retract it a few months later when it turns out. Yeah, no. In fact, it was a satellite. So
it was a satellite.
So we are seeing. So these are real cases that happen, and the point is that they're going to happen more and more often,
right?
As the number of satellites increases.
Yeah.
So something I don't know. Sorry, Dust. Something that just kind of popped into my mind as like a sheer that seems science fictiony enough that maybe that might be part of a help, not a solution. But like, do we need something akin to air traffic control for orbit, where astronomer, like
Absolutely.
where there is a database where astronomers can just go, this is where I was looking at this exact time. What did I see?
Oh, well, that's yes. So,
or am I talking about two different things? Yeah.
Right. There's two different things there. One is the space traffic management, which is avoiding collisions by telling the satellite owners, hey, you guys, you need to move right now. All right. And another thing is software for astronomers to mitigate the impact of this by figuring out, okay, I'm planning to observe tonight in these positions. What times am I going to be messed up by satellites passing over? And can I optimize an observing schedule to minimize the amount of times I get zapped by a satellite?
Yeah, it's almost like you need collision avoidance for the incoming radiation that you're detecting and the satellite going over. Different type of collision avoidance.
Yeah, it's like a cola hole, right?
Yeah,
and so and so actually I'm on a committee that's trying to spec that software and figure out what resources we need. I mean, because software takes time and needs to be done right, and it's going to require money, right?
It needs data too.
And exactly, it needs maintenance, it needs all these things, and so we're looking at that. We're looking at software to automatically flag satellite trails. We may not be able to remove them, at least to the level that will let you measure things that were underneath them, but we may at least be able to automatically mask them so that software that is detecting exciting things doesn't look at the trail and go, oh, I found something exciting, right?
Right.
And so there are various things that we're looking at to do the best we can if we have to live with this, while we're still pushing to kind of have some sort of regulations that make the situation less bad.
Yeah, mitigate it.
and so that's a big part of what I'm working on right now is figuring out exactly what software already exists. Some of it is very specialized, like it works for this particular telescope, but not for telescopes in general. So how do we migrate to a solution that will help us in this world where we are continually being plagued by these satellite streaks?
Right.
And all this, the sort of prediction, when am I going to be hit, it only works up to a certain number of satellites, right? Because there's a certain number of satellites in which the answer is always yes. The answer is you're always going to be hit.
When are you going to get hit? Yes.
Yes, right, exactly. And so when we get into that regime, then there's really not a lot you can do. And when you get to the regime of not only are you going to have a streak, but you're going to have 5 or 6 streaks on your image, and so then the data just becomes really hard to deal with.
Yeah.
So,
Chris,
yeah,
can I hop in? I wanted to ask, because Jonathan, you mentioned this conference that you've been preparing for, and it's scientists and it's companies coming together to figure out how we can do to make sure we understand
and
this.
The public,
and deal with it. And the public.
Yeah,
is everybody coming? Because then you said China's also launching a big network of satellites.
We would love to reach out to the Chinese folks involved. They're in an early stage, and we haven't managed to establish connections with the right people yet.
Right.
But I'm mildly optimistic that we will eventually get them in the conversation.
Okay. Are all the other companies
because this affects
participating?
them too,
Yeah.
right? I mean, this isn't just
that's exactly right. And so, although they have the same problem that we have, which is that the relative weight in politicians' ears of satellite companies and the scientists is not the same.
Right.
So we'll see, but yeah, I think it's going to be a very interesting conversation. What we're trying to do as well is reach out. We have a community engagement process now that's going to be part of this conference, where we're trying to reach out to people around the world who are not necessarily involved in space, but care about the night sky,
right?
And get them involved too in sort of making the discussion about, to what extent is the visual environment of the night sky part of international environmental concern.
Right.
Yeah, and I mean, to not just the light pollution. The light pollution element in terms of you guys for astronomy, because this isn't a situation that can just be solved by moving every telescope into space. I mean, not only is that incredibly expensive to do, right? I mean, it's not viable.
It's just not viable this century, I think. Maybe next century.
Right. Yeah. So I guess I kind of hate to ask it this way, but like you said Starlink has been, and SpaceX has been really responsive in that regard toward making changes. Maybe still ways to go, but they've been responsive. What about OneWeb? We just had the 8th flight for them. We had their earlier thing, like you were saying, I think it was January of this year, where they said, okay, we only need like 6,000 or 5,000 or something.
Only.
Right. And
like that.
That's a big improvement.
Right.
I mean, they're only recently kind of getting their act together after having been, in a hiatus due to the bankruptcy.
Right.
And so they are, I think, a little behind the curve in getting involved in this. But I'm, at one level, I'm optimistic that they want to help. I have chatted with a number of the OneWeb engineers. They're all very, we want to do what we can. Oh, but you want us to move your orbital height? No, that ain't happening.
Right.
And so whether they can do anything that will really address this remains to be seen. And yeah, so I think it's an open question. I do believe that in their hearts they want to help, but that doesn't mean that they will.
Yeah.
So,
then there's reality. You ask them to triple the mass of each satellite, and they're like, "All right. You paying for that? Who's doing that?"
Right.
You know?
Exactly. So, and there's so many constellations planned now, right? Trying to engage with each one each time is sort of a whack-a-mole job, right? That I think that's why we feel like there really has to be discussions at the UN level that flow into national regulations and
Right.
things like that.
So sort of exactly to that end, Kate Summers was asking, is there any governing body or state that says what you can and cannot send to space, or how much can be sent, and what kind of guidelines could be enacted sort of in the manner that they were when lunar exploration was agreed to? Sort
Right.
of that framework.
I mean, there is the Outer Space Treaty, right, which says
Right.
with due regard to other. There are space sustainability guidelines coming out of the UN, and so there is a licensing process in each country. So in the US, that's the FCC and the FAA, and so there are international and governmental methods of oversight into what can be launched. So if you're a private company, you can't just say, oh, I'm going to launch this today and not have to go through some kind of permitting process.
Because wasn't there a company that got in trouble, like a U.S. company got in trouble because they went to
Swarm
India and did that?
Yeah,
Yes.
Swarm, that's right.
Got denied by the FCC and launched anyway.
Yeah.
And they got a big fine for that. But they've made nice now, and they're being good citizens now, and they're continuing to launch their small. They have tiny little quarter U, less than CubeSats.
Oh wow.
And so the concern there was trackability, and they've added like little radar reflectors on their satellites so that they're more easily tracked.
Gotcha. So it's almost a case where the satellites were too small to keep track of, as opposed to
Right.
too big. Like
Exactly. There's a kind of different case.
All right.
This is a big expanding business area of what we'll call IoT, data relay. So Internet of Things devices have relatively low bandwidth compared to Starlink, which is trying to do broadband internet.
Right.
And so you can use just these very small satellites to relay the data.
Yep. All right.
Yeah, indeed. So where I feel like the conversation, I feel like the constellation that never gets talked about though is the Amazon one for Kuiper. Where do they sort of fit into this into this view in your regard?
Right, and we're talking to them too. I mean, where they fit in is they haven't started launching yet.
Well, there you go.
Right, and
Not a problem yet.
You know, well, no, you know, they are, you know, the filing that they have. Das came back.
Yeah, I'm here.
Yeah.
I think I kicked a power cable. Sorry.
he was like, "That's it, I'm out."
Yeah, I'm
We're
out.
talking about
I'm
Amazon.
done.
I have stock. No.
So the proposed Amazon constellation is only a few thousand. Right?
Only.
But not in the tens of thousands. Now that's just because they only did one filing and not the sort of second generation filing. They may still have plans for the bigger one. They just haven't requested it to FCC yet. So I think they're very much in the same game. Their so far proposed satellites are in the lower orbits like Starlink, so that's good. And so they're not, you know, the dominant thing that we're most worried about for most purposes are the higher orbit constellations, which right now is OneWeb and China DW. But there's still concerns about the lower orbit constellations, especially for asteroid surveys and things like that.
Oh, that's interesting because a lot of our because you'd be capturing them too, right? In the field of view for asteroid surveys.
Right. Well, the thing about asteroid surveys, right, is particularly for near Earth objects, you do them at twilight,
right?
Because they're near the sun, and you have wide areas to try and catch them. And you know, so it's like all the worst possible things come together, right?
Right.
You're looking for things that aren't moving with the rest of the stars too. So the entire sky is moving like this, and then something's not following that motion, and that's one of the things. But
That's
satellites
right.
do the same
in
thing.
Typical, the streak size is very different from a satellite streak size, so that's less of an issue.
Right. Okay.
What we get with the asteroid surveys is we get the high orbit satellites, the ones beyond GEO. Including stuff that isn't in the satellite catalog because it's been lost because Space Command Space Force doesn't care about the beyond GEO stuff, and so we keep finding these things and saying, "Oh, we found an asteroid. Let's give it, you know, a designation, blah blah blah," and then 2 weeks later, no, okay, that's a booster from an old Chinese moon probe.
Right.
And it's not in solar orbit, it's in deep orbit around the Earth-Moon system, but the rate at which it moves across the sky is very similar to that of an Earth asteroid. And so that's a whole different challenge that we're facing, but less of a problem than the mega constellations.
Right. All right.
Yeah. So you mentioned that there are a lot of guidelines and sort of regulatory things that we're seeing coming out of the UN to the extent that the UN can enforce those. But like, if the UN says like, hey, like, we actually think, you know, these mega constellations aren't necessarily for the best use of all because it's interfering with astronomy. Like, if they were to say something like that, or say like, you know, we'd really like you all to relook at these mega constellations. I mean, the reality is though that the US, China could just ignore them.
That's true, but I think if they came out with a recommendation that, you know, say, you know, motherhood statement that, you know, the night sky is part of the common patrimony, common heritage of humanity,
right?
That therefore states should restrict the number of satellites above a certain brightness, you know, in a certain altitude range, you know, something like that. That would eventually get flowed down to FCC regulations, and in the same way that debris recommendations have gotten flowed down to debris assessment reports that you have to fill in for the FCC, and so So I don't think anyone is going to say. I have some colleagues who would, but I don't think it's going to go anywhere to say no. Shoot them all down, you know.
Shoot them all down. Well, now you just have more things to track if you do that. Satellites,
exactly, or ban these constellations. I don't think that's going to happen.
Have like a moonraker thing going and eating satellites or something.
But some kind of management of the brightness of the night sky at different levels, you know, like no more than X at this brightness, no more than Y at that brightness. And I think we're going to have to also have, not for astronomy, but just for space traffic management, just for collision avoidance, restrictions on how many satellites can you have at each altitude in LEO?
Right.
We really have to have, and Marie Bajaj at the University of Texas has been arguing, and I completely agree with him about you know, the carrying capacity of low Earth orbit, and the fact that we're now at a position where you really have to have that discussion that it is not. Space is big, but it's not that big.
Yeah, it's not.
And especially in LEO.
I almost said it's big, but it's not infinite. But then I'm like, well, actually, should I say that? The space around Earth is finite. Let's put it that way.
LEO is not infinite.
Yeah.
And so you really are at a point now where, SpaceX is going to own that, you know, 550 kilometer plus or minus something, right? And so, you know, that's a shell of space that no one else can pretty much use.
But that's also very close to sun synchronous altitude as well.
Well, sun synchronous satellites are in LEO, at different altitudes, right? So they can be anywhere from 200 to 1200. But the thing about this 550 altitude-ish, right, or I would say 500 to 600, is it's a sweet spot because you still re-enter on a reasonable couple decade time scale, footnote, but you stay up long enough that it's, you know, you can make some money for a few years.
To be useful,
right? And so it's kind of like a useful active life period altitude range. And so there's actually, when you do that calculation, right, of how much the space satisfies that, it's not that, it's pretty finite.
It's like the prime real estate almost, like.
Right, exactly. It is the prime real estate. And then the footnote is climate change is actually decreasing the density of the upper atmosphere and increasing orbital lifetimes. And due to various atmospheric chemistry things I don't really understand. And so actually you may have to bring your satellites lower in the years to come because the drag is not enough to bring them down. Your calculations on how long it would take for the drag to bring them down are going to be wrong.
Gotcha. Well, then you just install a big drag parachute behind each satellite, and the astronomers have to deal with that. Like, you can't win.
Right. Yeah. Well, but I mean, that's always the case in aerospace engineering, right? You're making trades, right? You can never win one extreme or the other. You always are like trying to thread your way through the trades to find a solution that can work.
Gotcha.
And so sort of, there's a great question here that I think is a perfect transition between this.
With a mic, apparently.
There's a great question here from
Can
Tim.
you hear me now, folks in the chat?
I mean, watching your levels have been okay. I've seen a couple people, but I think it's just a mic difference thing. I'm not too worried about it.
Okay.
Yeah.
Great question from Tim. That's a good transition between this conversation about mega constellations and into our sort of miscellaneous grab bag period here. So Tim is saying that his university in Estonia is currently working with the European Space Agency on EstCube 2, which is a demonstrator for deorbiting space debris via plasma breaking. He'd love to hear what Jonathan thinks about this emerging field of space tech and orbital safety.
Yeah, no, I think ADR, active debris removal, is definitely going to be a big thing in the years to come. And the reason is this: when we talk about orbital debris, there's the small stuff and the big stuff. And so the small stuff, there's 20,000 catalog small objects from disintegrations of satellites, and then maybe 100,000 to 1 million things too small for the radars to see. And then there's the big stuff, which is the 100 kilogram and up to many ton stuff. There's about 4,000 or 5,000 objects that are dead satellites and dead rocket stages. And in fact, the larger number of small stuff is not the stuff I'm most worried about, because although it's the stuff most likely to hit you on any given day, it will get over time cleaned out by orbital decay. A small piece tends to have a higher ratio of its surface area to its mass, and therefore it's more like a sail than a cannonball. It gets slowed down faster. And also the below, certainly the below, the 1 centimeter kind of stuff could be fatal to a satellite, but it's not going to cause the mass debris event when it kills that satellite that a collision between two big ones will. So when we've had 2 major debris events in 2007 and 2009, the Chinese anti-satellite test and the Iridium Cosmos collision. And those 2 events between them, basically overnight, I mean, over 2 nights, but increased the amount of catalog debris by 50%.
Wow.
Just from 2 events, right? And so you do not want those kind of events. And that is the thing that drives the sort of Kessler runaway of, turning the LEO into like a shrapnel belt that we couldn't use anymore.
Right.
And so if you can, so the priority is to remove the big dead chunks. That's the point.
Right.
Because that reduces the rate at which you have these really bad collisions. And so rather than wasting your time blasting the tiny stuff with lasers or something,
right,
put your money into the fleet of space garbage trucks that takes the big chunks away. And so we're now at a phase in ADR and active debris removal where different companies and organizations are trying out different technologies. So we have the EstCube 2 that you mentioned. We have ELSA-D, which is the Japanese UK astroscale company that is going to practice this magnetic plate experiment that it has. We had Surrey satellites remove debris a couple years ago, which tried a harpoon and a net and other technologies. And so, so people are, which is great, right? People
Sure.
are playing with
Ideas.
ridiculous ideas and to see what works best. And I think we're now, and China's done at least one experiment. They haven't said much about it. And there's another one that Arianespace has launched a little experiment where they have a little color disk that they're then going to try and capture somehow. And I think again with a net. And so we're in a experimental phase now that's going to mature, I think, in the next 3 or 4 years into sort of decisions about what the real technology is that should be used. Maybe there's more than one. And so I think in the 5-year timescale, we'll start to see deployment of, all right, let's actually now figure out, let's actually now do some real debris removal, not just experiments on debris removal.
Right.
And let's figure out how we can fund it, which I think has to be through taxes on space users.
Right, right.
And let's see how we can make it legal through the UN, because there are all these issues about the worst, as Darren McKnight at Leo Labs has shown, a lot of the worst, if you sort of pick which ones are the biggest threats, right, in various metrics, it turns out that that's a lot of old Soviet rocket stages in 900-kilometer LEO orbits. And so if you're not a Russian company, you know, how you're going to get permission from the Russians to get rid of their garbage.
Right.
And are they going to be happy for you to do that or not?
Yeah.
And so the space lawyers are just salivating at this. It's like, oh, we're going to have so much fun negotiating this for the next 20, 30 years.
Yeah.
And I'm like, no, you need to do it now. You know. Yeah. So I think this is going to be an increasingly important aspect of space activities in the years to come.
Right. And the paying for it seems like it's going to be a big deal, because it's not like you're going to go out and, I've picked up this piece of debris and, it's worth this much money so I can sell it and pay for my garbage truck, right? The money's got to come from somewhere, and it's not going to be because you recovered it. It's going to have to come from, like you said, taxes on space users or something like that, because it's not a profitable business. There's no reason to run that space garbage truck. It's just, for the good of mankind.
Yeah,
well,
exactly.
Somebody's got to pay for it.
So that's right. You're not gonna, selling the scrap on eBay is really not gonna cut it.
Yeah.
Yeah. Especially if it's buyer collects.
Buyer collects. I know we're always, every time we do one of these shows, we always run out of time. There's no way that we don't run out of time, but we still have one huge topic to talk about here.
Oh, two actually.
Two other huge topics to talk about. Mega constellation, space debris. Chris, are we good to move on to the next thing here?
We are indeed.
Okay.
And it's everyone's favorite thing, because we've talked about big satellites, we've talked about black holes, we've talked about telescopes, and now we're going to talk about a thin little line at 100 kilometers named after Karman.
Wait, where? Where is it?
Well, I'm going to say maybe. So, Jonathan, I have a very humorous question, but go with this where you will. Karman line, are you pro or con?
Well, I'm pro Karman line, but I'm con Karman line being at 100.
Right.
Okay. Yes.
And so I would argue that historically Karman line was not at 100. This is a relatively recent idea in the past few decades that you should just say it's 100. It's not the definition of the Karman line.
Right.
And so we're talking about, where are you in space or not? Are you a space traveler or not? And so Karman's idea was, you're in space if the gravitational forces dominate the aerodynamic forces.
Right.
And that's the key idea. And he was talking about lift, and I use drag, but that's a detail.
Could have called it pressure.
It all comes out in the water. It's all pretty close. And so the feeling in the sort of 70s and 80s, I think, was, the atmosphere varies and we don't really know exactly, so we should just use a round number when we talk about it. And it turns out that the atmosphere does vary, but higher up. and that it doesn't vary very much down near where we're talking about at this boundary of space.
Right.
And so in 2018, I published a paper where I showed that, in fact, if you do the Karman calculation with modern atmosphere models and with a good range of estimates of satellite properties, that the effective Karman line, the point at which aerodynamics stops winning against gravity, is about 80 kilometers and not 100.
Right.
And it's 80 plus or minus 5, maybe plus or minus 10 on a bad day, but it's not plus or minus 20, right? And so if you take the Karman argument seriously, the number you should pick is somewhere near 80. And if you look at the actual data, if you say, where do satellites actually re-enter? Well, if you're in a circular orbit, they actually re-enter up at about 130 or something like that, 130 kilometers. But if you're in an elliptical orbit, you can actually stay in an elliptical orbit with a perigee of 85 or 88 or something like that, multiple orbits around.
Right.
But if your perigee drops below 80, you never actually reappear. Yeah,
you're coming home.
It always re-enters and burns up if it gets below 80. And so there seems to be, and if you're doing an active deorbit, right, like yesterday the Cygnus cargo ship deorbited itself over the Pacific, where does that break up into pieces? It's somewhere between 60 and 80 roughly.
Okay.
It's a little low, maybe closer to 60 for the breakup, but it's sort of down in that range. It's not up at 100. And so putting all of these things together, looking at, where do things actually survive and where do they not? And where does the Karman physics say that the boundary should be? It became clear to me that 80 is a better number than 100. So that's what I published, and I'm sticking with it.
Yeah, and of course,
and 80 kind of matches, because there was something that I thought was very, very interesting looking at some things from Roscosmos in particular, and I'm using them because they mark the Karman line with the boundary, and there was that whole Soyuz MS-10. I don't know, did they get there? Did they not?
Right.
But one thing that's very fascinating to me is they mark entry interface for the Soyuz lower than 100 kilometers. So like their boundary when it's coming back in is down near, I think it's in the low 90s or upper 80s, but
okay, I thought it was 120, but that may just be
it was very fascinating to me that there was a boundary difference for them on that. Yeah,
well, that's right. And it, obviously, right, as a scientist, what boundaries you pick depends on what questions you're asking. Right. And so there are other possible boundaries of space that you can work with, and it is ultimately somewhat arbitrary, right? But you do need to pick one, I think, for a lot of reasons, and to the extent that the Karman one is the one with the longest pedigree and its correct value, I argue, is 80 and not 100.
Right.
Then I think that's what we should go with.
Yeah.
Then I think I know this question that I had prepared, but it also came from one of our members, Durai, who was asking, so what do you think about the suborbital guys fighting about who's going to be in space first?
That's why this is a big thing, right?
And this is why like having a uniform boundary definition that we can agree to can become important, because we're going to have the battle between Jeff Bezos and Richard Branson here this month if all goes to plan, but Richard Branson only goes up to about 83 kilometers. Jeff Bezos in the Blue Origin capsule will actually cross 100 kilometers. So who wins?
So, I mean, my practice for 30 years now has been I add to my list anyone who goes above 80.
Okay.
And as a historian of spaceflight, that's what I choose to use as an academic. And so I will be counting, both of them as astronauts, even though Bezos will, of course, claim that only he is and Branson isn't.
Right.
And that's, so for my records, for my database, for the Jonathan Space Report, right, I need a uniform definition.
Right.
And So that's why I looked into the physics of it and decided what I thought the right definition was. Others may disagree. So yeah, I mean, it's obviously now important to Virgin, and clearly, Virgin's happy with my definition, right? And it makes me happy because this argument makes my paper more important.
There you go. A lot of citations coming up, right? Like
that's the hope. Cite my paper.
Cite my paper. Actually, I have a paper on this. I mean,
Yeah.
it's not just a bunch of billionaires out here playing Calvin ball, like making up the rules, and no, I won because the flag is blue today. Like there is, as a space historian, a need to define what it is, and you've done that. You've done the research, and you came up with 80, right?
Right, and not everyone has to agree on the definition, right? But you should say what definition you're using and be consistent with it.
Right.
And I'm, obviously I feel like my definition is better and everyone should adopt it.
There's a paper.
But everyone should, or even if they don't adopt it, they should cite it at least, so that my citation count goes up. But that's okay. Other people can disagree.
Well,
But I think you hit on something about the importance of this line that also touches, especially with how space and the access to space is changing and is set to change very rapidly this month if Virgin and Blue can achieve what they want to do. And later this year, it will change even more if Inspiration 4 does indeed get off the ground this year. Astronaut, I mean, technically anyone who does travel above that line would be an astronaut, right? Just like technically anyone who's ever been in an airplane would be or a hot air balloon would be an aeronaut. The difference being we don't call ourselves that, and we would give much more emphasis to the pilots on the plane and on the aviation side.
Well,
what are we headed for in these definitions of humans who cross this line but aren't, and I say astronaut, I include cosmonauts and taikonauts and the professionally trained folks.
Right. Let me just say about cosmonaut first. I think it's the most stupid thing ever to have different words for the people in the same job from different countries.
Yes.
Right? And like if I meet a fireman from France and I refer to him in English as a pompier, I just sound like really pseudo.
It's just Le Fireman, isn't it? I thought it was just you put Le in front of it, like.
Cosmonaut is the Russian word for astronaut.
Right.
And you don't need a different word for every country. That's just silly. So then, what does astronaut mean? Words in English have different senses. I would say I'm happy to use astronaut in the sense that we use flyer for aeronaut, right? You talked about aeronauts, but it used to be if you talk about flyers in 1920, you would mean mostly pilots, right? But now I say I'm a frequent flyer. Now no one thinks that I'm actually at the controls of the 747, right? and so I think it's fine for the word to evolve in that way. And I actually kind of like, so the question is, we need a word for the professionals who are part of the crew and not passengers. And as an old science fiction fan, I'm personally partial to spacer.
Okay.
I think I'd say, that on the Virgin flight, Mazzucci and McKay are spacers. And the 4 Virgin employees who are going along. A shout out to my friend Sirisha Bandla. I'm so excited that she's. I'm not so excited about Richard, but I'm really excited about Sirisha. So I'm happy for them to be astronauts, but not spacers.
Gotcha.
Marginal because they are employees. They are doing professional roles. So they're space travelers. I see someone in the quotes in there, that's another way you can say it. I think much fewer people would object to space traveler, but astronaut is. We already talk about people like Jake Garn being astronauts, the senator who flew on a I was talking about Bill Nelson, the current NASA administrator, right? So I think the historically it's already established. I think that battle's already been lost, and the astronaut covers this. It's more like flyer than it is like pilot.
So it's like spacer versus astronaut, somebody who travels among the stars, even if that's 81 kilometers, versus somebody who works among the stars is almost the other thing that we need.
Exactly. Well, even works as a driver, right?
Yeah.
It's like maybe, if you're the doctor on the space station,
right?
You're not, and you just came up as a passenger. Now we think of that as crew.
Right.
If we ever get into a stage where you have space settlements that are, like people are effectively civilians, that they're living their lives there, right? Kids growing up there. Then a job on the space station is not necessarily crew. Right.
Okay.
What if you run the Starbucks on the space station?
Are you an astronaut?
Right.
Are you crew or are you or not? Right. And so I think you have, if you think out a couple hundred years, right, and try and make sure that that's what I always try to do. I always try to take my definitions.
Yeah. Useful in the future.
Run them forward a few centuries to see if it's, if they're general enough.
Right.
Okay.
All right.
I think that's a good distinction. Like, I lean more towards the side of somebody who's working there. So if you're working the Starbucks, I would still call you a spacer because you live and work in space. You're not just passing through, right? But then you get like the commanders, the pilots, the people that are crew. I guess.
What about in Musk City on Mars?
See, you're an astronaut getting to Mars, but then once you land there, I used to be an astronaut, but now I'm a Martian.
If you grow up in Musk City. You've
never left Mars. You're just a Martian.
You're a Martian, right? The same for our lunar colonies.
Yeah.
And then this is where like we could just devolve into our expanse conversation
Right,
about where it goes from there.
But we still need to know what's in orbit.
And this is what I was going to say. This is one of the questions that I had prepared, but I want to read out a couple of them from our members as well, because Michael Curtis has asked, what's the lowest orbit that can be sustained for at least one orbit without having to do a burn? And then another person is asking just literally, what is the definition of an orbital flight? So we'll take both of those separately because I have those I'm leading to something.
There's a big question here. There's a big question.
So the lowest orbit, again, like I said, if you're in an elliptical orbit, you can have a perigee, closest point to the Earth, that's only about 80 kilometers plus a tad.
Right.
And that you can, if your apogee is up at 30,000 or something, you can go around several times or even for a week or two.
Right.
At that without re-entry. If you're in a circular orbit, then the lowest that's been sustained for a day or more is 135 kilometers, I think. And that was a Chinese satellite called Lixing 1 a few years ago.
Okay.
And generally, and that was sort of had active propulsion, so that maybe that doesn't count. But so
is it flying or is it orbiting?
You're going to re-enter pretty quickly if you're below 150 if you're in a circular orbit, and that's just. But it's not that you're at 150 and then suddenly you burst into flame and re-enter.
Right.
It's that at 150, the drag is so much that the time it takes for your orbit to shrink from 150 to 80 is very short.
Right.
Right. And then you burst into flame and re-enter.
I like that. It's not like 150 and the satellite's like, oh God.
Like suddenly.
Right.
It is that like that below 80.
Right.
So then I guess where some of these questions are coming in. So we have that. So am I understanding you correctly? Like your argument would be that in order to be technically defined as being in orbit of Earth, you have to have a perigee that is at least slightly greater than 80 kilometers if you are in an elliptical orbit, and a circularized. How does that work? Yeah.
Right. So the first thing I want to say is that words in English have multiple meanings.
Yes.
Right?
Yes.
And so there's orbit sense 1, orbit sense 2, orbit sense 3, right? And so asking what is the definition is a little like the wrong question. And if you go to my website and look at my space glossary, planet4589.org/space/gloss.
I got it.
Then I go into all the. I have a lot of these things where I have orbit, space sense 1, space sense 2, and so on, to try and bring out this idea that it's okay to have multiple definitions. You just got to say what you're using at any given time.
Right.
Having said that, yeah, my for orbit, I generally mean an orbit that does not intersect the Earth's surface. I mean, as a astrodynamicist,
Okay.
right? You know, if I you know, throw my pen in the air and it falls down again, that's still an orbit. It's an orbit that, you know, didn't complete because it hit the surface of the Earth. But usually we mean an orbit that does closes, that you make a complete orbit, right? And so yeah, if you're in, but what about, you know, if you go to an orbit that's like at 1,000 kilometers up circular, but then halfway round you make a deorbit burn and you come down, so you never completed the orbit,
Right.
And so for me, but you can still define an instantaneous set of orbital parameters at any point of that orbit,
Right.
in which the perigee is positive, right, is high enough. And so I think you're absolutely right. They say if your perigee is above about 80, then it's reasonable to say you're in orbit around the Earth.
Your perigee,
as long as your apogee is less than 1.5 million kilometers.
Right. Because then you're leaving, right? Like,
Because then you're leaving. Yeah.
And so that's what I use. And anything below that, if your apogee is above 80 and your perigee is less than 80, then you're suborbital.
okay.
Okay.
And if your apogee is less than 80, then I could just call you transatmospheric. So I only use suborbital for things that are actually at least at some point outside the atmosphere.
So me throwing
okay.
a baseball into the sky isn't suborbital, it's transatmospheric.
Exactly. Unless
Unless
your muscles are a lot more impressive than I suspect.
Then they look like
So all of this is sort of built a little bit to has built a little bit to a couple of questions. Obviously, if a planetary body that isn't Earth does not have an atmosphere, you could classify it as being in orbit as long as it doesn't slam back into the surface. But Earth isn't really. But would you say that's fair?
Yeah,
to Earth, because like you said,
I'm still struggling with the definition of space on an airless world.
Right.
Yes.
And I've actually figured, and usually when you struggle, what that means is that there's actually two concepts that you've conflated that you need to separate out.
right.
Oh.
Okay.
And so if you go to space in this glossary, I don't know if you can find.
I can scroll down. I tried to search for orbit, and that was a bad idea. That did not just take me to the definition of orbit, because it says orbit 18,000 times.
So basically, I now have added a space senses 4 and 5, and here we go. 3 and 4, yeah, and so there's so if I'm on Mars and I'm inside the Martian atmosphere, I'm not in space.
Okay.
But if I'm on the moon, I'm in the airless spatial regions between worlds, which is my sense 3 of space.
Yes.
Right.
So in that sense, if I'm on the moon, I'm in space. But sense 4, the regions in which orbital travel is possible. Right. And then if I'm on the surface of the moon, I'm not, because my spacecraft might hit a mountain.
Right. I've
Right.
had that happen in Kerbal all the time. It's like,
and so the question is, how high do you have to be in the moon so that you don't have to worry about hitting topography?
right.
And I think you add also, as you orbit, you're being perturbed by the mass cons and by radiation pressure from the sun. And so what's the maximum that you might get lowered during a single orbit?
Right.
That needs to be calculated by somebody. Maybe me, but I'm happy for someone else to do it.
But I'm busy, right?
To figure out exactly what that line is, the safe orbital travel line.
Yes.
Space definition for the moon.
Like a stable orbit or a safe, sustainable orbit. There's all sorts of adjectives you can put on the front of it.
And so yes, non-litho breaking orbit.
Right.
Yes.
And so the and then there's this broader sense of space in which you and I are all right in space right now.
No, technically, yeah.
We're all we're the Earth is in space, so we're in space, right? And that's one. So you have to be you have to be okay with there being multiple senses. and just being specific about which one you're using in a given discussion.
Gotcha.
So at the buzzer, this is we've got a little we've got a few minutes
You know
leeway,
how it goes.
like where the boundary of space is. So we got a little bit of leeway here.
We have to decide, define
yes.
when NASA Spaceflight Live ends, and it just depends on which sense we're talking about. Sometimes it ends at 4:30, sometimes it ends at 4:35.
When you get too hungry.
It ends after the final question, and I don't know if this will be it, but it's my final question. So this has all been building toward this conversation. So SpaceX has their orbital flight of Starship coming up, in which they will purposefully not actually insert the Starship into a stable orbit. They will leave it low enough so that it comes back in on that first go. They don't have to worry about firing the engines for deorbit.
Right.
Is it fair to call that an orbital flight, especially since it even geographically doesn't return to the same point on the ground?
Yeah, exactly. And that's, it's a marginal case, right? It's a marginal case. And so, and it's not clear to me what the orbital parameters would be.
Right.
SpaceX, please publish them. But I'm guessing what they're talking about is something where the perigee is positive, but not above 80.
Right. That's what it sounds like from what we've seen.
And so I have a category in my database for that, what I call the U, or unnumbered launches. Where I have, because I always like to look at these liminal cases, right? And there have been about 30 or so such cases in the history of space exploration where things have got into this almost orbital. Like usually when there's a launch failure, right, it's not even close.
Right.
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 And so that, but there've been some test flights and some launch failures that have been, in this marginally orbital case, and so it's going to get one of those designations from me. And so then, that's the key, right? You categorize it and you go, okay, it's in this box. And if you like this box, include it. And if you don't like this box, don't.
Right. And we need the information from SpaceX. We need SpaceX to say, here's the plan.
I need to know the perigee value that it has at apogee, right? Because actually the changing all the time. So the most interesting thing is when it's at apogee, what's its instantaneous perigee if you pretend that their surface didn't exist?
Right.
Right? and that number sort of gives you the shape of the ellipse at apogee, and that's what tells me what box I put it in.
Gotcha.
From
the standpoint of classifying and reporting and making the historical record reflect, here's what I've defined this, and here's the reasons I defined it this way. That's the really important thing you keep talking about. We can make decisions and we can classify things, but being able to back up why you classified it that way is really important.
Exactly. And the argument is never, this is why it's true. The argument is always, this is why I think this is a sensible and useful choice.
Right.
Right? Because nature doesn't have these boundaries.
Right.
Humans create boundaries, and we create definitions and boundaries that are useful to us. And so you want a boundary where if you wiggle it a little, things don't go crazy.
Makes sense. Chris, I think we sort of got into covering what we wanted to cover there at the end. This is specifically with the Starship orbital test flight, and it sounds like we're missing some information on that before we can really classify it. For now, all we can do is sort of guess and say, well, if it's this, and if it's this, and if it's that. But did we miss anything? We've got Jonathan here. That was your last question. Any door hangers?
Well, I guess, Jonathan, a curiosity thing, because you said SatCon 2 that's coming up in next week or in a couple of weeks was also, it wasn't just for astronomers and the launch industry, it was for the public. Are there ways for the public to watch that if they were so interested?
Absolutely, or even join in the engagement part of the conference.
Cool.
So if you Google SatCon 2 with no space between the N and the 2, I think you find it. And it's operated by Noir Lab, which is the optical astronomy US organization. But yeah, SatCon 2, July 12th to July 16th. And the registration's open now and it's free.
I've got this up. Let me see. I've ended up on the AAS.org. Yeah, I did SatCon 2 just like you said with no space. I'll put this link into chat if y'all are interested in checking this out. So here is the link right there. Paste it over. And sorry, I was on the wrong computer when I started typing there, and so it changed the scene instead of typing SATCON. That's what the brief loss of signal was. That was me typing S for standby instead of S for SATCON. So resolved quickly. But
I think they've got a link there to the actual registration page, because that's the older one.
That's SATCON 2 workshop, constellation. Well, SATCON rogue recommendations. There's a lot of links here. There's a form.
Oh, no. Okay, that's the older one.
Okay.
So let me see if I can find, if you do SATCON 2 registration, that might find it.
I can do that. There's register for satcon.com.
That's something else.
Okay.
Yeah. This one, Wirelab one, down where your
this one right here.
Yeah.
Let's see here.
That's the one.
That's the one we're looking for. Oh, there's home registration, agenda, that sort of stuff in there. Okay, so I'll put this link into chat.
That's the one, folks. So SATCON 2 Wirelab was the key, I think.
There we go. Yeah. All right. So that's coming up July 12th, I think you said. I get the date right. All right.
I'm not ready yet.
Well, we better let you go so that you can continue preparing for SATCON 2, right?
Right, exactly, yeah.
All right.
Please, if you're interested in this issue, check it out, because it's our opportunity to engage with the public. And you probably don't want to go to my session, because my session is the computer algorithms working group. It's going to be boring, but the policy session and the community engagement session should be really compelling, I think.
Good deal. Well, all right. Chris, if we haven't missed anything else, I think that's going to bring us to the end of this week's NASA Spaceflight Live.
I think there is, like always, I tried to hit as many of the questions as we could. We had some really awesome questions, I know, from our chat, but as always, tried to hit as many of them as we could. And Jonathan, thank you so much for coming back. It was wonderful. Absolutely wonderful.
Yeah.
It's always fun to chat with you folks. So yeah, thanks for having me back.
Good deal. As always, again, folks, our special guest this week was Jonathan McDowell. I will say lots of things. We talked about Chandra X-Ray Observatory, cataloging what's going on in space, planet4589.org, the long-running space catalog of things that happen in space. If you're interested in what's going on, make sure I'll put this link over there as well. But publishing these newsletters, keeping track of what's a launch, what's not a launch, what's in orbit, what's re-entering, all the different things you do, Jonathan. Thank you for all of your work. And there's that link in chat, y'all, if y'all want to go and check it out. And thank you for joining us again this week. Also on Twitter, you can find Jonathan. Planet4589 is your Twitter handle as well. Same as the address that I just put into chat there. But make sure y'all head on over and check that out if you're interested on what's going on in space. Also with us today, Chris Gebhardt. Chris, you're up above me right now. Assistant Managing Editor for NASA Spaceflight. Thanks again for hopping in here today. Always a good time.
My absolute pleasure.
All right. And lastly here, I'm John Galloway with NASA Spaceflight. I'm clicking on the things after a little bit of a hiatus there. Was down working on some things away from the studio, but I'm back now. And we will be here. Coming up next week, we're watching what's going on. Looks like the testing down at Boca Chica, those road closures got canceled. Not sure if they're going to start those again or what's going to happen. Launches next week. We're in a launch drought, aren't we, Chris?
We are in a bit of a launch drought. There's nothing from the U.S. next week. I think the next two launches are a Chinese weather satellite and another Chinese mission,
right?
Tiananmen, and then Virgin Galactic.
That's right.
Potentially.
I guess I said launch drought, and I was like, well, we're not covering anything from the Cape. We don't have anything from Vandenberg, but there's still things happening.
The Nauka launch got delayed, right?
It did get delayed,
Yeah, forgot to cover the sensors.
I think there'd be on a checklist somewhere, huh?
Oops. Yeah. Well, you make fun of it, wait until,
It was only noteworthy because it was Nauka. That was the only reason. It was noteworthy, yeah.
Right. But that is going to bring us to the end of our show today, folks. Let me make sure, as we do, massive thanks to our members. We're able to do this because y'all keep showing up. I know that we don't read all of the super chats and stuff like that during the show. I see a lot of super chats that came in. Folks, thank you so much for the support, making it so we can keep doing this. Also, our members who are continuing to make the font on this page smaller and smaller. We really appreciate your continued support. That is one of the reasons. This isn't one of the huge, oh yeah, Starship is doing a thing today. But this sort of report, we love bringing you this good information with interesting people here on our weekly show. Be sure to check us out next week as well. But for now, we're going to go ahead and shut it down. Jonathan, again, thank you so much for joining us today. It's always a pleasure talking with you.
Always a pleasure. I'll try answering some of the questions in the chat later.
You did that last time. Like all of a sudden Twitter's going off and you're going through some of the questions that we didn't get through live, and you were answering a ton of questions on Twitter. So I know you're busy. Thank you so much for the time and dedication there, for real.
Yes, thank you.
Love you guys. Take care.
All right, good deal. Well, for now, we're going to go ahead and roll the credits, and we will see you nerds later. Thanks again for watching, y'all.
All right.
Propulsion continues to be nominal.
The chamber pressure looks good. Toggling up.
Roger, roll, Atlantic.
Water towers, fly! Yes!
Tango Delta nominal.
Flight SE off. Bring in SE off.
Yikes. You bet. Concur. We don't need any more of these.
Y'all are still here? Why are you still here? Go home. The show's over. Wait, we had one more thing to do, didn't we?
Was this is like the stay after the credits thing,
We
right?
did.
And you
It
might see
is.
something special.
People that stayed after the
Jonathan,
credits.
you have a new boundary to space that you wanted to talk to us about.
Yes. So, the one I've proposed at 80 kilometers, I believe that's the way to go. But there are alternatives, like I said. And one of them was suggested to me yesterday, and I sort of worked on it a little bit. And I'm calling it the Ripley line. And the Ripley line is, how high do you have to be so that the air is so thin that nobody can hear you scream? And because as
Did
we
you
know,
calculate that?
in space, no one can hear you scream, right? And so therefore, if no one can hear you scream,
You're in
must be
space.
And so it turns out, right, that there's a minimum auditory threshold that corresponds to pressure fluctuations in the air of about 20 micropascals, and then how loud can you scream? Well, as a theoretical physicist, I don't really know, but I can get that the absolute maximum you can imagine is if you bounce the air density down to 0 and back up again, and so the amplitude can't be more than the air density. So if you say, where does the air density get down to 20 micropascals, that's about 250 kilometers.
All right.
And so my first crappy estimate of where the Ripley line is 250 kilometers, but it's probably lower if you do it properly. So that's, you heard it here first. That's the new space boundary, and other people have pointed out. You asked me, Chris, when do you know you're in orbit? And so the answer is, if you're sure that having nuked the place, that everything is okay, then you must be in orbit.
Then you must be in orbit. So you heard it here, space billionaires. You can cross whatever 80, 100 kilometers, but until no one can hear you scream, you're not truly in Ripley space.
Exactly. So I think that's a good post-credit scene note to end on. And I'm sure I will see you guys again at some point.
Sounds good to me. Now the show's really over. Not running the credits, not running the outro twice, but we will see y'all later. We had to put that in at the end.
Bye, everyone.